In this video, we'll be finding volume using slices of known cross-sections. The only thing we need to know is that volume is defined as the integral of the area of the cross-section with respect to x or y. So if it's in terms of x, we'll take slices perpendicular to the x-axis, and for slices perpendicular to the y-axis, we'll look to have the cross-sectional area in terms of y. So again, the only thing we're going to need is the cross-section in terms of x or y. Then we'll be able to integrate across the bounds. So there's several different ways we can slice our volume. So our first example. Imagine the base of a solid is bounded by y equals root x, the x-axis, and x equals 9. Cross-section perpendicular to the x-axis are squares. What does that mean? So let's first sketch out the base of the region. So we have x equals 9, and we have the x-axis. And let's shade in this space. And what you're going to have to imagine after this, imagine a solid coming out of this base, and each cross-section is a square. So what comes out, the length of the square is going to be equal to each side, so it's going to come across looking like this. And then there'll be another piece over here. So there'll be, we can draw several of these pieces. It doesn't matter where we draw it, but we'll have squares either way. If you can imagine a loaf of bread, sometimes that helps you visualize things a little bit better, and that's what those look like. So each slice, the only thing we're concerned with is the face of that slice. So we can choose any of these slices, and I have one drawn off over to here as a square, and we can look at that base right here, and that base is the y value right there. And notice our thickness, since it's perpendicular to the x-axis, is dx. And the height of this square, since it is a square, we have equal side lengths, is y. The only thing we need to determine is the area of this face, which is clearly y squared. So this piece of the volume, the one slice, we can refer to as dv, and that's simply going to be the area, which is y squared, times the thickness, which is dx. And if we sum that up, we have the volume is going to equal the integral from 0 to 9, those are our bounds, of y squared. And remember, we're told that y squared is equal to root x. So we could make that substitution, y equals root x, and we're left with the integral from 0 to 9 of root x squared dx. This is something we can go ahead and evaluate. We'd have 0 to 9. Root x squared is simply x dx. And we can use the power rule to integrate this. So we'd end up with 1/2 x squared evaluated from 0 to 9, which would give us 9 squared 81 over 2 minus 0. So we're left with a value of 81 over 2. And we'll be able to use this for the remainder of our examples as well, because we're going to be referencing this square cross-section. So now imagine if the slices perpendicular are no longer squares, but it's a right isosceles triangle with the leg on the base. Let's also do a sketch of that. So we're going to go up to 9. We have our bounded base right here. Here's the region. Many times we'll be asked just to find the area of the base first. And then again, imagine coming out of here are right triangles, leg on the base. So this would be a right angle coming out here, if you can imagine that. And then this is going to be slanted out. And then the same idea, right angle right here, going back in, and then same thing. And now the nice thing is we don't even need this picture here. We just need to have an understanding that we are just concerned with the face of that cross-section and being able to find that area. And again, here we have a side length of y, which I'm going to relate to this picture right here that I have set up as y. And since it's a right isosceles triangle, the height of that is also y. And if you think about it, a right isosceles triangle is just half of a square if you cut it using a diagonal. So we know the area of this right isosceles triangle with the leg on the base is simply 1/2 y squared. So our piece of the volume will be dv equals 1/2 y squared. And again, our thickness is dx. I don't want to forget that. So we have dx because it's perpendicular to the x-axis. And again, we know that y is equal to root x, so we could make that substitution and look at what the actual volume is. So remember, the idea of dv is we're summing them up to get the volume, so we're going to sum up the other side, and we'll have 1/2, and again, y squared, so we can say root x squared dx. And this can be simplified a little bit more. We'll say 1/2 we can always pull out. So whenever you have a right isosceles triangle, it's going to be just 1/2 times the side length, and in our case it's root x, and it's going to be squared, so it leaves us with x dx. So it's really related to the last problem where it's just half of the side length squared. Another case. Now let's say it's a right isosceles triangle with the hypotenuse on the base. So now I'm looking here. So rather than draw the picture out, we're going to realize that this is perpendicular to the x-axis. And we know this is our y value. And we just need to determine what the area of this face is. What is A? And we know that we can look at this several different ways. We could drop an altitude and use 45, 45, 90s, or we can kind of be a little smart about it. We can think about a square, and if we were to draw two diagonals, and if we were to look at this bottom piece right here, we would have a right isosceles triangle with the hypotenuse as the side length. So if we do that, we'd understand that we simply have a fraction of the square. We have 1/4 of y squared is our area. So rather than draw the picture out, let's just go ahead and say dv is going to be equal to 1/4 y squared. And again, our thickness perpendicular to the x-axis is going to be dx. Or generally speaking, we're going to have 1/4. The integral from a to b, or in our case, our limits of integration are the same, 0 to 9, of our side length squared with respect to x. And then I'm just going to go ahead and write what our side length is. It is root x. So we can go ahead and simplify this and see that we have 1/4 integral from 0 to 9 of x dx. And again, we're just going to have a fraction of the answer we had earlier. Now, one that's a little more challenging for people, where it's not necessarily an obvious fraction of the square, as if it was equilateral triangle. So again, I have my slice ready, and we're going to say this is our side length, that is the base that's perpendicular, and this is our thickness, dx. So now we understand, since it's equilateral, we have 60-degree angles everywhere, and if we drop an altitude, we'll have a 30, 60, 90 triangle. So across from the 30, we'll have half y, just for that little piece there. Our altitude will be root 3 over 2y. So the area will be equal to root 3 over 2y times 1/2 y, which is going to simplify to root 3 over 4y squared. Again, it's a fraction of the square. So if we were to write this as the piece of the volume that we're looking at, it's equal to root 3 over 4 times our side length squared, y squared dx. Or for our particular problem, the volume is going to equal, I like to put root 3 over 4 out here, and we'll go from 0 to 9. And our side length squared, again, I'm going to leave it like this. So you can see whatever our side length is going to be, we can just substitute that in. Or we can write this as root 3 over 4, the integral from 0 to 9. Root x squared is simply going to be x dx. And again, we have a fraction of our last answer. Another common cross-section that seems to come up is the idea of semicircles. This seems like it could be a little more challenging, but it's not bad at all. So imagine this is our entire side length is going to be equal to y. Then we just have to know, how do you find the area of a semicircle? Well, it's 1/2 pi r squared. So we just need to identify our radius. And our radius is really just half of y. So we can write radius is 1/2 of y. So we would have 1/2 pi times 1/2 y squared. And this simplifies to pi over 8 y squared. So for our problem, if we're summing these up, our piece of the volume, dv, is going to equal pi over 8 y squared. And again, my thickness is dx because it's perpendicular to the x-axis. So our volume for this problem is going to be pi over 8, again, another fraction from 0 to 9 of our side length squared with respect to x, and our side length is root x. It could be any function that they're looking at, or it could be the difference of two functions. And that is going to simplify to, again, pi over 8, integral from 0 to 9 of x dx. So again, it's going to be a fraction of our original answer. For our last problem, we're going to take a completely different look. So now we have something bounded between two curves, y equals x minus 4, y equals ln of x, and our slices are going to be perpendicular to the y-axis. So let's see what that looks like. So again, here is my region that's bounded, but now when I take my slice, I am cutting it horizontally. So my thickness is dy. Make sure I make that nice and clear. So our thickness is dy. So our formula is still going to be based on a semicircle. So the volume is going to equal pi over 8 integral, and whatever we're summing up from. So in our case, we're going from the bottom point, our slices are perpendicular. So we're going from A to B, and I already took the liberty of finding those points of intersection, and we're going to be using the y values. The bottom one is approximately negative 3.98 and so on. And point B, we're going to go up to about 1.749 and so on. And then we're just going to need our side length squared, and it's going to be dy. So to get our side length, it's just the length of the side. So we can see here it goes from the equation y equals ln of x across to y equals x minus 4. Y equals ln of x is on the left, so we're going to have y equals x minus 4 is going to be on the right side, and y equals ln of x is on the left. So it's always going to be right minus left or upper minus lower, depending on what we're looking at. But since we are in terms of y, we need to transform both of these equations to be in terms of y. So the equation on the right, if we solve for x in terms of y, we get x equals y plus 4. And for y equals ln of x, solving for x, we get x equals e to the y. So now we can just substitute in, knowing that the side length is going to be equal to the right side, which is y plus 4, minus the left side, which is e to the y. So let's write our answer over here. So we're going to have volume equals semicircle. Our fraction we're going to use is pi over 8. The integral from, and there we have our negative 3.98. This is something you would store in a calculator if you needed it, up to 1.74. So bottom to top. And then our side length is right minus left was the y plus 4 minus e to the y. And remember, that quantity is squared. Don't forget that. And that is with respect to y. So again, here we were only asked to set up but do not integrate. That's quite common. So no matter what your cross-sectional area is, you can just substitute that in, and integrate is what you're going to do. It could be in the form of an equation, or it might be something you have to find, but these are some of the more common cross-sections you'll see.